Hello, everyone, and welcome back. We continue with the second advanced part of our summer school, Quantum Horizons, Developments and Opportunities, which we organize as a school workshop where world-class experts and great speakers of the world offer you the excellent series of specialized lectures. This evening, we again have the honor of joining us as a speaker, Professor Barry Sanders from the University of Calgary in Canada. Professor Barry Sanders is also director of the Institute for Quantum Science and Technology at the University of Calgary. He's also a distinguished associate member of TÜBİTAK Research Institute for Fundamental Sciences. Many of you, of course, know Professor Barry Sanders from the first preparatory part of our school, where he gave an excellent lecture on quantum computing. This evening, he's going to give a great talk entitled Quantum Control for Fast, High-Fidelity Two-Qubit Gates. Barry, good morning. Please come and begin your talk. Thank you for joining us again.
Thank you very much. It's a pleasure to be back. Just make sure you can see you can hear me fine and see my share screen, right?
Yeah.
Okay, great. All right. So last time I gave a general talk about quantum computing. This time I want to get into a particular problem that I've been working on for about 13 or 14 years now. And it's really techniques for quantum control, both for ions and neutral atoms. And the title you've got is similar, but not exactly the same as this, but I'm speaking exactly about what was advertised. So the particular stuff I'll report this time is done with 3 of my PhD students, Saeed Shakib Vedai, Archismita Dalal, and Eduardo Paez. They've done a lot in preparing this presentation. Okay, and then the work I'll talk about, some of the work I do on this is machine learning for quantum control, and some is on global optimization for quantum control. And the references down here are specifically optimization and not machine learning. So the earliest one that I did was the Physical Review letters back in 2013 and a follow-up in 2015, and then elaboration in Physical Review Applied. There was a New Journal of Physics paper that I'll mention as I go through on alternative methods, but basically the question of whether the choice of global optimization method really matters. Physical Review A in 2020, and I have a new paper out on the archive about a week ago that talks about the neutral atom case. The ion trap work I'll report here is not yet out, but it should be on the archive in the next week or so. And then these are the various agencies that have funded the work. NSERC, which is the Canadian science body. MyTax supports internships with companies, Queen Elizabeth Scholars, CryptoWorks 21, Compute Canada, and Alberta government. Okay, Okay, so the left is showing you what the talk is about. I begin with what I always like to begin with in a technical talk, what I call ACNE. It's the aims, claims, novelty, and importance. So I'll begin by making it clear what the whole talk is about, and then the rest will be details. I'll talk about quantum control for ions and quantum control for neutral atoms. So even though ions are just charged atoms, the techniques are different for dealing with control. And then the approach that I'll use will be mathematical. I'll give a mathematical description of how we turn quantum control into an optimization problem and then into a feasibility problem. And I'll explain what I mean by that. And then I'll give you the results for ions and neutral atoms and draw some conclusions. And the results are good. I'm proud of these results. So I'll tell you about them and conclude that they're good results. On the right, you can see various ways to reach me on social media, and there's a picture of Calgary at the top. So the aim and claims. So I'm just going to take a bit of time to talk about what this means. The aim is to design feasible 2-qubit quantum gates for scalable quantum computing with atoms. either ions or cold neutral atoms. I'll use the letter Q often to write quantum for short. I'm not concerned in this presentation about single qubit gates. It's really making a 2-qubit gate that entangles two-level systems. Feasible, so optimization problems is to get the best. Feasible means good enough. So our feasibility condition will be based on fidelity, or rather infidelity. And design is really designing a pulse sequence that will deliver a feasible 2-qubit quantum gate. And my criterion is it has to work in the lab. So we work closely with experimentalists to make sure that what we design is experimentally relevant, not just a proof of concept. And then we have 3 claims to make here. One is that we are able to design the entangling gate. This gate is discussed in Sorensen-Molmer papers from the late 1990s, 2000, or late 1990s. And it's just a combination of an identity gate on 2 qubits and a NOT gate on 2 qubits, and that generates the Bell state. So if you start with the state 0, 0, then it generates the state 0, 0 plus 1, 1. And I don't bother with normalization if I can avoid it. So gates are unitary, pure states are normalized, and then I always just leave it out just to make things look nicer. And it's an easy exercise to normalize. I'm calling that Sorensen-Molmer gate the XI gate. And then for our ion trap, we have done theoretically, and we're going to report soon experimental results. I'm not an experimentalist, but experimental collaborators, where we take the best in the state of the art, where there's a gate time tau, which is currently about 254 microseconds, and we improve it by reducing it to less than a factor of 1/7. So we get a 7-fold improvement in the gate time, and we maintain the infidelity. And I'll define the fidelity later, but it's just the overlap of the resultant state with, or the square of the overlap of the resultant state. Well, no, I'll say it's the overlap of the resultant state with the pure state, the pure Bell state, 0, 0 plus 1, 1. And so we fix the infidelity. And then we also are designing 2-qubit gates for neutral atoms. And in particular, one that we've been simulating is cesium-133, and we're able to cut the gate time by a factor of 3 and the infidelity by a factor of 2. So we have different targets in each case. And these are important because 2-qubit gate performance, both how long it takes to execute. So the longer it takes to do a 2-qubit gate, the slower the quantum computation is. And the worse the fidelity, the less likely we are to be able to scale. Okay, so what makes our work different from what others do? So we refer to SOTA, S-O-T-A, as state-of-the-art. So the state-of-the-art is what exists before our work, and then we've been doing various techniques to get things to work better. One of them, the first bullet point here, is that we have a good model in both cases. So we've been developing our models to take into account the actual physics of the system and match to experiments, and we have no fitting parameters. So we make sure that everything we plug in, experimentalist tells us the parameters, we plug them in, and then we can't fit things to make better results. So we incorporate into our ion trap model and atom off-resonant transitions, photon scattering, vibrations, and laser intensity fluctuations. That's for the ion trap case. Another thing that we do is we Fourier analyze. So we optimize in the time domain, and then we do Fourier analysis to check that to make sure we understand the physics. So whatever we get in the time domain, we do a Fourier transform to analyze the physics. On the machine learning side, which I don't talk about, same thing comes about. So one of the difficulties in optimization and machine learning is we get results we don't understand. And so in my group, we spend ages trying to understand what these things are telling us. And I'll show you how we use Fourier analysis and why it's so useful. The next thing is that we do robust global optimization for 2-atom quantum gates in open systems. So we make sure that we have an open system description, i.e. we use master equations, not just Hamiltonians. And we do global optimization. Almost every other group works with what's called greedy. They look for local optima, and local optima are good if there aren't that many constraints. But for quantum computing, there are a lot of constraints to make it really good. So we do global optimization techniques, which puts us apart from most groups. And we also make sure things are robust. So when we get solutions, we then allow error bars on our parameters and make sure that the performance is robust against parameter drift or uncertainties. And then for the neutral atom case, we have started to use, instead of optimizing, we're using transitionless quantum driving. It's a technique that Michael Berry proposed a number of years ago. And so we're able to start with adiabatic solutions and then make them better with transitionless quantum driving. And we're hoping that can be tested experimentally, but so far the results, we're okay with our results, and we would like to get a test done. And that transitionless quantum driving work is the one that just appeared on the archive about a week ago. Our work is important because feasible again means it's good enough. And so we write down the fidelity that's required for scalability. A lot of subtleties in that statement, but roughly that's the idea. And so we start off with a feasibility condition. And by dealing with the problem in terms of feasibility instead of optimization, it helps us a lot in getting to a good solution. This is explained in our new Journal of Physics paper from 2018. The techniques we develop here are good for other applications and other quantum computing settings, such as superconducting. Some of the early papers that I did were on superconducting systems. I left that behind for the time being because the models aren't that great. So I did work on superconducting for a while, and then I went back to atomic physics because I understand it better, and it's easier to get the models very accurate. And then we uncover pulse design principles, e.g. by spectral analysis. And this is important because when we get our solutions, we then extract the physics, and then we're able to figure out from a physics point of view how to do things. And getting the physics intuition helps us a lot in reconciling theory with experiment. Here's a description of the ion trap scheme. This is taken from a paper by Choi, Debnath, Manning. I tend to just do a shorthand where ING, I just superscript the G. TION for Shen, I just superscript N. So that's a shortcut. I use Figet, Gong, Duan, and Monroe. This is using I explained last time, the short DOI. And so you can see here, there's an ion trap. There's 5 ions in this trap. Our simulations are done for 7. These gray regions are electrodes that hold the ions in place. And then they form what's called a Wigner crystal by Coulomb repulsion between the ions, and then electrostatic repulsion from the electrodes. We can drive it by Raman beams. So there's what I think of as a blanket that covers all the ions, green, and you can see it's correctly coded here. So the green here is the 0 to P transition. Sorry, throat's drying up, just a moment. Okay, and then the red and the blue beams are specifically targeted to different ions. So you can pick different target ions. They're directed by an acousto-optic modulator. And this is realizing, I don't have time to go into it in detail, but this is the idea of the Sorensen-Wolmer gate, that the 2 ions, one can be blue detuned, the other red detuned. And then the phonons that are created by detuning form what's called a bus that connects them and makes a 2-qubit gate. So the 2-qubit gate can be realized by entangling the electronic degree of freedom with motion of the ions. In the Sorensen-Wolmer case, it was just the lowest order mode, so it was a rocking mode. But in our simulations and in current experiments and real-world implementations of ion trap quantum computing, we use all the modes. So in our case, we'll simulate for 7 ions. Therefore, there are 7 modes that all have to be considered in mutually coupling the ions. And I'll show you mathematically in a moment. The readout from the ions is done by fluorescence. which is picked up at a photomultiplier tube. And then we have a processing unit that adjusts the acousto-optic modulator, controls the beams, and the optimization or feasibility conditions. They come into how we're going to tell this processing unit how to handle the transformations. Okay. And then this is the neutral atom case, which I'll also talk about. So this picture is taken from a 2010 paper by Safman, Walker, and Molmer. Molmer's the one I mentioned, who did the ion trap gates. He's also done this. In this case, it's neutral atoms that are trapped in an optical lattice, ideally exactly one atom per site. And the atoms are held in place by dipole forces. So just detuned laser beams that crisscross to form that two-dimensional lattice. And then the coupling, once upon a time, people imagined it by collisions. Nowadays, the coupling would be done by Rydberg atoms. So Rydberg atoms are highly excited alkali atoms. So they're hydrogen-like, one outermost electron. And by having large dipoles, distant dipole-dipole interactions are strong. And in the right, you can see what's going on. So this result is out of a 2020 paper my students Dalal and Paez and I did with Mark Safman and with Betteroff. We actually deal with a couple of cases. One, we have the hyperfine splitting of the atom that gives the logical 0 or 1. In one case, this is normally done in experiment where we couple to the Rydberg level, so a very highly excited state, through a 2-photon or quadrupole transition, detuned from a P level, so some intermediate level. Or the other case that we analyze is strictly dipole, so we can go straight from 1 to near the Rydberg level. So the quadrupole is 2-photon transition to Rydberg level. The dipole is 1-photon transition. Each one has advantages and disadvantages, and we deal with both in our simulations. And then the B term is the Rydberg-Rydberg interaction. So that's the dipole-dipole interaction, which is a function of how separate the ions are. The neutral atoms are. And the capital omegas are Rabi frequencies and detunings, and the control is about controlling the Rabi frequency and detunings. They're time dependent, and we want to be able to control laser pulses accordingly. And then just to give you an idea of the experimental state of the art, which we advance on. So in Levine et al. In 2019, this is the short DOI for the reference. They consider a one-dimensional array of 10 rubidium atoms. The fidelity that they get is 0.974 for a gate time of 0.4 microseconds. And in 2022, so very recently, there's a two-dimensional array of 49 cesium atoms. So it's 7 by 7, and they expect a fidelity of 0.955 and a gate time of 0.8 microseconds in that case. So you can see that the 2D array is worse than the 1D array. And in simulating and trying to optimize what goes on, we need to consider that the 2D array tends to be worse. It just gives more degrees of freedom. Okay, so this is the kind of thing that we want to beat. And again, SOTA, remember, is state of the art. So that's the state of the art method. Those are experimental results. Okay, so here's what we do. There's a control pulse, and it's a time-dependent Rabi frequency, which I mentioned here. So we discretize time, and then what we do is we replace the time-dependent function by a vector, and then we have a number of time segments. This turns out to be a hyperparameter in our optimization. We have a detuning, which is time-dependent. We replace it by a vector. Essentially, what we're doing is converting a continuous optimization problem to discrete combinatorial optimization. We imposed maxima. So this is what I mentioned. A key point here is that we have a lot of constraints. If we don't constrain it, then the greedy or local optimization methods of others work well. But we believe and can show that these constraints are really important. So we believe global optimization is necessary. This is the, we constrain omega max. This is essentially telling us there's a bound on the laser intensity. Rabi frequency is the dot product of the atomic dipole with laser frequency. So we bound the laser intensity. We bound the laser intensity But in experiments, this is done by calibration. They just shine the whatever laser as strong as they can get, they shine it on the system, and then they measure Rabi flops to estimate the omega, and then we bound it by how strong the laser can get. And we also bound the detuning. And then what we do is write a Hamiltonian, and the Hamiltonian is a function of this vector representing a discretized version of the Rabi frequency function, the vector representing the discretized version of the detuning. Alpha is just a set of constant parameters that represent the environment and in the ion case, the trap, and the optical lattice in the case of neutral atoms. And our robustness condition is that we allow variability of these constants. And so we check that our results aren't overly sensitive on the choices of constant parameters. And then we have, strictly speaking, a time dependence of the Hamiltonian. And so we're able to construct the Hamiltonian for the system. And then we have non-unitary processes that feature either into a master equation or into a stochastic average of solutions to a master equation. So we incorporate spontaneous emission, power fluctuations with a laser, collisions between atoms, photon scattering like Rayleigh scattering, and thermal fluctuations. For the neutral atom, a lot of these don't matter. We can ignore them. And for thermal fluctuations, for the case of the ions, we treat it within the master equation. For neutral atoms, we treat it statically, where we assume just random positioning of the ions over some distribution. And so we do an averaging after. So the way we treat non-unitary processes differ depending on the system. Then we express everything as a quantum master equation. So rho is the density matrix for the atom and possibly other degrees of freedom. For the ion, with 7 ions, we have 7 ions that are each ion's multiple levels, and we have 7 phonon modes, so 7 motional modes that we have to take into account. So our matrices are very big in both cases. And that means that we have to be careful in our computational, how we use our computational resources. Then we integrate, and I mentioned to you, the N is just TION abbreviation, so equation, integrate the evolution, and we get a solution after some time tau, which is the gate time, in terms of the choice of Rabi frequency and detuning and the constant parameters. And then our, if we consider an optimization problem, we want to be able to deliver the best infidelity. So the fidelity is the overlap of the resultant state with the target state. For the ion trap and the neutral atom, it's a Bell state, 0, 0 plus 1, 1 for the 2 qubits. And the infidelity is just 1 minus the fidelity. And so we want to minimize the infidelity and do a search over omegas and deltas such that we can minimize. So we're searching over a pair of vectors to find a solution that delivers us minimum I, but we don't actually do that. We replace it by the feasibility problem. So we introduce a feasible I or I threshold value, and then we halt the computation when the infidelity reaches the required bound. Okay, so our feasibility problem can be expressed mathematically as saying, given a pair of ground state atoms, they can be neutral or charged, so they can be ions, each driven by intensity and or detuning modulatable Raman beams over a gate time tau. So that's a given. We're not optimizing over gate time. We're given a gate time and then optimize the other terms. And then we actually find a feasible values for Rabi frequencies and detunings constrained by omega max is effectively due to a limit on the power of the laser. Delta max is a limit on how much detuning is possible through the instruments. I max, it should be I max is correct. A limit to how much infidelity is allowed. And tau max is the gate time, the maximum allowed gate time. Then we, I mentioned we discretize. And then the discretization, when we make that vector, the length of the vector is m, that's how many, we chopped up our continuous time into discrete time. We discretize it, and how many there are is a hyperparameter. And probably most of you aren't aware of the difference between parameters and hyperparameters. But when we do optimization, feasibility, machine learning, et cetera, we often have models that have tunable parameters that aren't physical, and we make choices of those. Those are called hyperparameters. So chopping a continuous function into a discrete steps is not physical. That's what I think of as hyperphysical. And so so the number of segments is a hyperparameter. And then in our global optimization, our go-to for a number of years, back 13 years ago when I started, we would use particle swarm optimization. And in those days, off-the-shelf code wasn't really available. We gradually switched to differential evolution. We have our in-house code. But my 2018 New Journal of Physics paper shows it doesn't really matter a lot which code is used. I used to think it did, but we have good in-house code and we love differential evolution. Differential evolution is an advance over genetic algorithms. Genetic algorithms are global. Differential evolution is an advance over it. And essentially, instead of genes for genetic algorithms, we use chromosomes and have some mixing. I won't go into the details here, but our work uses differential evolution, which we find performs better, but I'm not making the claim it is better. Okay, so what does the Hamiltonian look like? This is the ion trap case. So I'll just give you an idea of what we're optimizing. So the time-dependent Hamiltonian, it can be thought of as so there's an H bar in front scale, and then we sum over J, where J is the index of which ion. In our case, we take 7 ions. We have the Rabi frequency for each ion, which eventually is an experimental parameter. The experimentalist can give us data on fluorescence coming out of shining the laser on the ion, and then we're able to write down the Rabi frequency for each ion, calibrate that. We have a cosine of delta t plus phi j, that's the detuning that we control, times time, plus a phase term. And in fact, we also, well, that's good. And then we have the raising operators. So this excites, this is a hyperfine excitation in the ion. So, and then this, oh, and by the way, this is not the Rabi frequency, strictly speaking. It's an effective Rabi frequency due to Raman transitions. So, whereas Rabi frequency is single photon, it's a 2-photon extension. This is discussed in the Sorensen-Volmer work from the 1990s. And then we have e to the I. Beta j is a position operator for the jth ion. In fact, we add here a detuning term that allows us to take into account laser drift, and then the phase term, and then this HC is the Hermitian conjugate. And I mentioned beta j of t is the position operator. So over here, this is a Lambdicki parameter, position for the kth mode. So sorry, I shouldn't say position, it's the canonical position. It's a quadrature for the kth mode. And so the position operator is a linear combination of canonical position for different modes, and then Lambdicki parameters in front of each one. And the Lambdicki parameter just quantifies an overlap between the mode function, the kth mode function, and the jth ion wave packet. And xk, this is the quadrature operator. It's just a sum of annihilation and creation operators that incorporates a detuning from transition frequencies. And then we initialize, so the ions are never starting in the 0,0 state. They start in well, they can start in the 0,0 state, but the modes don't start with no phonons. So we give a thermal distribution, that's the Planck distribution for phonons in the kth mode. And down here, I've got a reference to Sorensen-Volmer, because a lot of information I give here is explained in their paper. Okay, when we incorporate the master equation, we put in what are called Lindblad terms, jump operators for motional heating. So this heats up the kth mode, dephasing due to motion. I mentioned the scattering of photons. We have Rayleigh scattering and laser dephasing that couples in via the sigma z. Raman scattering effects, laser intensity fluctuations here, cross-Kerr coupling between vibrational modes, and an Adler-Towne shift, also known as an AC Stark shift, which is a pulse-dependent drift of laser detuning. So the laser detuning can change. So we incorporate these into our master equation. And now I'm going to tell you about the results. So this is the kind of result we get. So over here, this is what is done by state-of-the-art methods without global optimization. And on the right, this is what we get by our method. Now, the idea here is that we have to plug in constraints. So we put an upper bound on omega max, so how strong the laser can be. We're cutting down to a 35 microsecond gate time. I mentioned before, the state-of-the-art is 254 microseconds, and we want to cut the gate time by a factor of 7. So we cut it. We then wrote our own code to match the state-of-the-art method, and we find that we get a poor fidelity gate here, or if we change our hyperparameter to include more steps, we get more and more oscillations. So the existing method is poor at finding an adequate, high enough fidelity gate. And I told you before that the fidelities aren't that good even at 254 microseconds. In our case, we start to look for high fidelity. And so over here, with our method, we find this sequence. And if we change the hyperparameter, we start getting little oscillations, not the big oscillations over here. So basically, the finer the time mesh that you put on this system, the more and more frequencies that pop up. You can see down here frequencies. In our system, we don't get that. It's smoother, which is very good. Notice that our omega, the Rabi frequency scale in kilohertz, goes up to most about 800. Here it's double. So we're able to highly constrain the laser intensity, restrict the gates to about 35 microseconds, and get 0.9 up to 0.99 fidelity gates by doing it. And the whole trick in what we're doing is to make use of global optimization, to formulate everything clearly in that way. And again, I'm just going to say optimization. We really do it as feasibility problems, but physicists tend to think of it as optimization. So I'll just keep saying optimization just to make it friendly. And then down here, we do a Fourier analysis. So does state-of-the-art. Go is global optimization. And we look at the Fourier analysis of these different results. And we find that for short gates, the reason that the Rabi frequency climbs so much is because a lot of energy is wasted in generating these high frequencies, and they're not very robust to parameter variation. In our scheme, the laser power is going into the transition we care about, negligible higher frequency components. And so we're not losing energy into unwanted transitions. It's more efficient and a lot smoother. And down here is that variability. So we look at laser frequency drift. This blue curve is the state-of-the-art method with the infidelity. So we want infidelity to be really low. The infidelity at 0.1, well, goes down to about 0.01, which I mentioned earlier, has a very large delta. So there's a big effect. We've identified this as being due to a vibrational Bloch-Siegert shift. And in our case, we get a much lower Bloch-Siegert shift, and we find that we're consistently localized around that Bloch-Siegert shift. And so basically, if the delta varies a bit, which it will, we get a very good robustness close to 0. So our scheme is also more robust. The previous techniques aren't. Okay. We analyze why this is so. In this case, we do a phase-space analysis. So what we're doing here, this is the 6th mode. I mentioned we have 7 ions. So if we take the 6th mode and we start plotting in phase space how that mode evolves, with the state-of-the-art method, we can follow, say with the master equation, but you can see here, they don't join up. So the state-of-the-art method, by finishing the sequence without closing the loop, is leaving residual entanglement between the phonons and the ions. But it's important in the scheme to return to where you started to eliminate that residual entanglement. In our schemes, which we don't show here, we get complete closure. So we don't show it because there's no discrepancy in our scheme. So essentially our scheme will close it within our model perfectly. And that closure means there's no residual entanglement. And down here, we do a Fourier analysis. So in this case, we analyze what the free periods are. Over here, we find that these additional periods are leading to non-closure of that mode. So we're now able to understand that by not finding optimal conditions, it's just creating residual entanglement from cycle to cycle. And that's why it doesn't work that well. This is our approach to neutral atoms. So in neutral atoms, we've got the two cesium atoms drawn here. In this case, I'm just talking of, I said that we do two cases. We do dipole and quadrupole. That's the dipole transition, that's the quadrupole transition. And the idea is to find the time-dependent Rabi frequency that works well in this case, or in the quadrupole transition. And as I said, both schemes are used for neutral atom quantum computing. So we feel it's important to build methods for optimizing in both cases. And it's not hard to do them both at the same time. And all this is explained in the paper we just had put on the archive about a week ago. So the Hamiltonian, in this case, is driving a effective two-level system. You can see here, there's R1 plus the Hermitian conjugate and RR minus 1, 1. So this is the two-level system that corresponds to a superposition of the R1. So it's, we have the R1 transition, we have RR minus 1, 1. Okay, so this is like a sigma Z operation between the R and the 1, and then there's the driving term that's the superposition of both. So it's like a Bloch type Hamiltonian. And over here, the quadrupole one looks a bit more complicated. It involves an intermediate transition. And then we want to be able to do a controlled Z gate, in our case, not the Bell state generator. And for this case, we have the Hamiltonian on the first neutral atom, the Hamiltonian on the second, and then the uncontrolled Rydberg interaction between the two. So if both atoms are in the Rydberg state, there's a Rydberg blockade effect. And the Rydberg blockade effect is what causes a phase shift. So basically the controlled Z gate says, you have logical 0, logical 1, and then we want to make sure that if the initial state 0, 0, it goes back to 0, 0, 0, 1 goes back to 0, 1, 1, 0 goes back to 1, 0, but 1, 1 goes to a negative of the ket 1, 1. And that's achieved by exciting the pair of atoms into the Rydberg states at the same time for a long enough duration to pick up that phase shift. And then here we can study the resultant sequences. This result is our older one from 2020, where we use adiabatic methods. So we essentially propose an adiabatic gate. So let me just tell you, the previous techniques and what most people still do is they'll give a sequence of pulses that will drive a particular atom to some level, drive another level. So they might drive this to R, let them interact for a while, then drive them back. We propose doing everything simultaneously. And in this case, we use adiabatic methods. We come up with symmetric pulse sequences that have advantages. And over here, we're able to, by controlling the two Rabi frequencies here and a detuning, we're able to deliver a high fidelity gate. And then the omega-1, omega-2 refer driving both atoms at the same time. So basically we do both with the same laser pulse instead of doing sequentially two different atoms. And then over here, we have the Rabi frequencies on one scale and the detuning on another scale. And over here, this is where we do our robustness test. So we have on the vertical axis, delta I1 and delta I2. This is laser intensity fluctuations. Down here, we have detuning change, and we find that we get a very robust effect. So if we plant it at 0, 0, and 0, 0, our results are very robust to parameter drift. And then we're able, at least theoretically, for 1 microsecond pulses, achieve an infidelity of 0.003. And our system is also robust with respect to Doppler shifts. So we're able to incorporate motion into the neutral atoms and find, I mean, it's what we're doing here. So detunings and the intensity fluctuations are not a problem because of the improvement to Doppler shift effects. Okay, so then our most recent result is, this is the one that just came out about a week ago with my student Archisnita Dalal. That's the short DOI to look it up. And in this case, we deal with both the dipole and the quadrupole transition, but for brevity, I just put the dipole case. So we have one atom and the other atom. Omega tilde is just, we use the tilde to refer to the transitionless quantum driving effect. Let me just explain transitionless quantum driving for a moment. So I think most of you are familiar with adiabatic systems. So, you know, the idea of the adiabatic Hamiltonian evolution is that you make the system evolve slowly enough that if you prepare the system in an instantaneous eigenstate, it will remain in that eigenstate. So if you start off with a logical 0, logical 1, and evolve it adiabatically, then as the Hamiltonian changes, it's time dependent, the ket 0 will modify, right? The Hamiltonian changes over time. So the eigenstates change, but 0 is still the lowest, 1 would be the second lowest. And so if you prepare in this, it stays in this. And then the adiabatic condition is roughly that you have a time scale associated with the smallest energy gap. You have a time scale related to the rate of change of the Hamiltonian. And then there's a function of both. And then that gives you a speed limit. So the adiabatic condition tells you a speed limit on how fast you can change things. And we want to break the speed limit. There is literature on quantum speed limits, and it's faster than adiabatic. So we want to take the adiabatic solution as a first order solution and then speed it up. I mentioned earlier that Michael Berry wrote the seminal paper on transitionless quantum driving. And so there's a formula that we can apply to replace the adiabatic condition by a faster version that can give us a factor of 2 or 3, in our case, a factor of 3 speed up. And so we just simply take that formulation. So transitionless quantum driving is a big topic for the past decade or so. And we apply that. The trick that we do here, the transitionless quantum driving literature focuses on 2-level systems. In our case, we have multiple level. In this case, you can see 0, 1, R, but we also have P. We can have other levels coming in. And so what we tried to do originally is we did transitionless quantum driving on our whole system, and we got answers that were crazy, just pulse sequences that weren't physical. So we went back to the drawing board, and then what we realized is we need to identify a 2-level subsystem. In this case, it's the state 1, 1, and then the state plus, which is 1R plus R1. So it's the 1R, so R and 1 and 1 and R, and we drive that 2-level system. We applied transitionless quantum driving to that subsystem, and then we embed it back into the whole dynamics. So we're able to design physical pulses. That took us a year or 2 to figure out, so it wasn't straightforward, and I'm brushing it over in minutes. So if you don't get it, it's because I think it's not that trivial. But that's what we did. It's the details are in our paper. And then we're able to get sequences that are very nice for us. So what you can see here, the omega and delta curves are what we get, the dashed lines are what we get from adiabatic conditions. And then the transitions driving terms are the corrections. And so the transitions quantum drivings just reshape these pulses slightly. You can see more in the detuning, where we take a linear ramp function and replace it by some other function. And the combination of these two things gives us higher fidelity and much faster gate time. And then we're able to concatenate these. So we're able to then chop them up. And the way we speed things up is we take this better shaped pulse, and then we just, we shorten the time scale. So we can drop this by, say, a factor of 4, and then repeat 4 times. And that's how we're able to get much better performance. And then down here, we analyze populations, and we find that we start off with the 0, 0. So the 1, 1 is down here. And then we get our evolution. And what happens with the transitionless quantum driving is we get much smoother functions. And so again, this is a feature we keep seeing, that as we get better and better pulse design, things get smoother, and the experimentalists like it because the less things you tweak, the more feasible it is to do it experimentally. So we've developed our transitionless quantum driving scheme. So one of the novelties here is we've adapted transitionless quantum driving to be physically meaningful for higher dimensional Hilbert spaces, and we're able to design the sequences. And I'm just going to give you my my pedestrian way of thinking about how transitionless quantum driving helps. So imagine a waiter in a restaurant. So a waiter is carrying a tray. I'll use my iPhone as a tray. And then the waiter has a glass of water on that tray, and the waiter has to run from one point to the other. Well, if the waiter runs too fast, the force on the water causes the water to tilt and come out of the glass. So then the waiter has to slow down. And that's kind of where adiabatic comes in. You tell the waiter, look, run to the table, but don't run so fast that the meniscus of your water tilts higher than the glass. But a smarter waiter will tilt the tray. So if you tilt the tray, the meniscus and the water's tilted. And then when the waiter's running, the tilt won't spill out of the glass. And the transitionless quantum driving works a bit like that, that these modifications to the pulses are like the smart waiter who tilts the tray when she or he runs to the table. And so that's, over time, I've started to get some intuition about that. And then when I'm saying concatenating those, it's like tilt and then retilt and retilt. So a lot of the techniques that we build here, then when I want to get an intuition, I just start thinking about running, waiting on tables, running with glasses of water. Okay. And so over here, this is the concatenation. So we took this, we then made 4 in a row. So we took what we got out of transitionless quantum driving with better pulses. Then we do 4 in a row. The detuning looks bad, that it chops and comes back down, but it's related to a phase. So it's just a phase wraparound effect that doesn't look good on this kind of plot. And we're able to achieve, for the 1 photon transition model, gate times that are 0.12 microseconds, so much better than what is achieved out of other methods. Infidelity is only 0.003. Remember, these are just theoretical results, so they need to be tested. But essentially, we're able to deliver gates that are twice as fast as adiabatic gates, speed them up by a factor of 2 or 3, and improve the fidelity. And it's just done by concatenating these kinds of pulses. And then you can see the population jumping. The part I worry about here is there are sharp effects. So theoretically, it looks good, but there's always issues that will come up experimentally with changing moving dials, how fast you can move them. So we haven't yet mapped it over to an experimental realization, and we need to do that. Okay, I'm going to conclude. Let me just check. Yeah, good time to conclude. Leave time for questions. Okay, so I want to give you 3 takeaway messages. So number one important message is evolutionary algorithms yield feasible control sequences that surpass current alternatives for trapped ion and neutral atom quantum gate design. So I'm claiming here that our results are better than those of other people. Of course, don't never believe anybody. So you should check for yourself to make sure that you either accept or reject my claim. If you accept my claim that we're doing better, then the question is, how are we doing better? And the answer is, we're turning the problem into global optimization. We convert global optimization to feasibility. That's explained in my new Journal of Physics paper, why that's a good technique. And then we're applying evolutionary algorithms. I said that we use differential evolution, but in the end, I don't think it's that important which evolutionary algorithm. The trick is to get the hyperparameters tuned appropriately. So arguing over which model is less important than knowing what hyperparameters. So by using evolutionary algorithms with good hyperparameter tuning on feasibility formulated versions of the optimization problem, we are able to outdo other groups in designing those pulses, and we are collaborating with experimentalists to test. As a result of using this technique, we show that our 2-qubit gate is 7 times faster than both experimental and theoretical predictions. And we have experimental results that I'm not saying yet, but we should have a paper on the archive in the next few weeks reporting simultaneously theory and the experimental result. And for the neutral atom case, we can cut it by a factor of 2, but what we're very proud of is that we've cut the infidelity by a factor of 6, all other parameters fixed. So this is what I mean by better. 7 times faster gate for the ion case, fixing the infidelity, and the neutral atom case, cutting the infidelity by a factor of 6 while keeping the time the same. And our optimization techniques are useful for other quantum computing platforms. So that's what we believe. And and technique is very straightforward. And for people doing quantum optics here, it's really just taking standard Hamiltonian, standard systems, converting it to feasibility problems. So the physics here is all, I mean, for you in the audience, not all of you might know the physics, but what I'm telling you is well-known physics. I'm not introducing new physics here. But of course, to understand everything I said, you'd have to learn that. But the real trick is in being smart with how we compute. Okay, that's it. Thank you very much.
Thank you very much, Barry. That was very nice and very deep and exciting talk. Can we now take some questions?
It's okay with me.
There's one question in chat. Can you read this or shall I read for you?
Sure. Okay. How does the detuning have an impact on infidelity? The laser detuning affects excitation probability. Thus the Rabi frequency. Rabi frequency, okay, yes. Do not have any control on the electric dipole moment. The only way to manipulate the Rabi frequency, control the electric field of the laser, is this why we tend to argue detuning? I'm confused. Okay, I'm getting confused too. So, so let's see if I understand. So there's the control of the Rabi frequency, which is loosely speaking the intensity of the laser beam, and then there's a detuning, which is the frequency of the laser beam. So the detuning is really important, I guess, is the answer. Now, the way that it's typically done is we'll figure out theoretically what the transition frequency is, and then lock the laser to that. One of the things that we found in our modeling is the detuning is off. So we are claiming that the experiments have not always picked the right detuning, and that does impact on infidelity. We found numerically what the detuning should be, and I showed that here. This is the that curve with detuning, and so we found it, and so we're saying that by the state-of-the-art method, the detuning that's obtained is not right, and in order to achieve a better infidelity, much better infidelity, the detuning should be here. So your question fits this curve very well. And then the question is, why is this not at 0? What does cause the detuning? So we not only get a better value for detuning, but we also understand the physics of it. And the physics of that detuning is almost entirely the Bloch-Siegert shift. Let me explain that in case people don't know it, which probably is not well known. So over here, we have a raising operator, so it excites the atom, and a lowering of the atom. Oh, no, but that's not a good example. I don't think I have one here. Okay, let me just explain conceptually that what happens is, I'll stop the share while I make myself bigger, I guess. So the Bloch-Seegert shift comes as follows. So if you know the rotating wave approximation, so suppose you have a position operator and write it like A plus A dagger. And then suppose that you write the atomic polarization and write it as sigma x, or sigma plus plus sigma minus. And then what we do is we say, okay, there's 4 cross terms. There's A dagger sigma plus, A dagger sigma minus, A sigma plus, and A sigma minus. 2 of them, like A sigma plus, that annihilates a phonon and raises the atom, and its Hermitian conjugate are what we think about as energy conserving. And then the other terms, like A dagger sigma plus and A sigma minus, are energy non-conserving in the sense that we add energy to both the phonon and the atom, or we subtract from both. We do it in superposition. So it's allowed quantum mechanically to add energy to both or subtract energy from both. And roughly speaking, you can relate that to the energy uncertainty principle, delta E, delta T. So conceptually, you can say I can break energy conservation as long as I do it for a very short time scale. And physically, what that means is we don't see the effect because our detectors average over the coarse grain in time and they don't see it. But there is energy level shifts. So the Bloch-Seegert shifts are energy shifts due to these manifestly energy non-conserving terms. And that's what's responsible for that shift in delta. So the answer to your question is, yeah, detuning is really important. That the optimization techniques don't always get the detuning right, but ours seems to. And we think ours gets it right because the detuning that we find is exactly what we expect by the Bloch-Seegert shift, except we didn't expect it. We discovered it was the Bloch-Seegert shift after the fact. So our numerical simulations taught us the physics of how to get the detuning right. I hope that answers the question. Oh, he wants to be unmuted. I can't find him on my giant screen. Somebody else can unmute.
Can you hear me?
Oh, yeah.
I just wanted to be unmuted just to rephrase my question and faster. And can we address this answer to the phonons? Is it because of phonons? I mean, you said that we do not conclude that a detuning is not 0. It's slightly to the left, just on the figure you showed. Is this because of the phonons?
Well, so maybe my answer was too complicated. I mentioned it's to the left because of a Bloch-Seegert shift. It's actually a vibrational Bloch-Seegert shift. And there is a paper, I just don't remember offhand, but there's a paper that came out a few years ago called Vibrational Bloch-Seegert Shift. So it's due to the phonons, but it's due specifically to the effect, the averaging effect over the counter-rotating terms from the phonons. Does that help? Hello? Oh, okay, yeah, you wrote yes. Okay, now the question was from Alper. I think this time gain of your work would be great for a long life problem on quantum circuits or networks. Am I right or nonsense? Yeah, the answer is I don't know. So my focus is strictly on very technical. It's just, I want to help, like quantum computers still don't work that well. And I want to make sure that we're able to make faster, better gates. And my goal is to make them scalable. And I think the mathematical problems are getting very hard. So we have to get smart about how to deal with it. When you say long life problem on complex circuits or networks, if you take my approach, there would have to be a quantum control aspect to circuits or networks. And you don't mention quantum at all. So complex circuits or networks, if they're classical, I don't think my techniques help. But if they're talking about quantum circuits or networks, maybe. yeah, so that's the best I can answer that question.
So I don't see more questions. Barry, can we close here if there are no more questions?
Yeah, that's
Can we
fine. I
close
don't have
session
to.
here?
Yeah, I don't have to run like I did last time, but I'm happy to close.
Thank you so much for joining us for these two lectures. And I hope we will meet in person finally.
Okay. Thank you very much. It's a great honor to be here.
Thank you. Thank you. Bye.